First, I'd like to thank the organizers for the invitation. So today I'll be talking about my joint work with, based on my joint work with Ramanujam. It's about power maps, and the technique that we use is group actions. Let's look at what is a power map. So we are not going to look at any general group. We'll be restricting our attention to totally disconnected locally compact groups. We'll abbreviate them as TDLC groups. For any integer k, we define the power map, the kth power map to be this. Pk of g is g to the power k. So our aim is to understand, find structural conditions that would provide a necessary and sufficient condition for the power map to be either surjective or to have a dense image. So this will be our aim, to find some structural conditions on G that would be necessary and also sufficient, or sufficient separately also. So this one, in this direction, we recall on old result for totally disconnected locally compact groups done by Willis. This one, if G is a TDLC group, and if you have some kn power of some sequence of elements Gn that converges to G, here the condition is that Kn should go to infinity. Otherwise, this will not be very meaningful. So in that case, he has a notion called a scale that has to be 1 for that element. So that is same as saying that G would normalize a compact open subgroup of G. Small g, an element, the element that has this property, will satisfy a compact open normal subgroup of the group. Yeah, that I'll define what is, that's called the scale of G. I'll define later on. But in this situation of scale being 1 is same as saying that it normalizes a compact open subgroup. So let's, for the moment, think only in this way, that it normalizes a compact open subgroup. So the compact open subgroup, these are plenty inside this TDLC group. There are plenty of them are there. They all actually form a base for neighborhood of identity. They are a system of neighborhoods of identity in a totally disconnected locally compact group. The examples, typical examples are the linear groups over non-Archimedean local fits. So now we apply this result. How do we apply this result? So suppose we have one power map that has dense image, then for any G, using the continuity of Pk, you can find a sequence Gn that verifies this condition. Instead of Kn, we will have k to the power n, so k greater than 1. So this is simply uses the continuity of Pk to obtain this sequence. Now, by the previous theorem, we can conclude that each element, this is true for each and every element. So each and every element fixes a compact open subgroup. So our initial conclusion is that if the power map has a dense image, then each and every element fixes a compact open subgroup, normalizes a compact open subgroup. But does it tell anything new in this case when G is abelian? So it doesn't tell anything new, because in the abelian case, everything is normalized. Every subgroup is a normal subgroup. So it doesn't tell anything new for abelian groups. So we next look at this affine group. What is an affine group? Affine group, by affine group, we mean this one. So a simple example is QP or any local field also. Take all non-zero periodic numbers. So they act on naturally on the periodic vector space, one-dimensional period. This is a very simple affine group. So on this one, it definitely tells something about this, because this group has elements that don't fix any compact open normal subgroup. For instance, if you look at elements of this form, r comma 0, where r is in QP star, and r has periodic absolute value 1, less than 1 or greater than 1, not equal to 1 case, but less than 1 or greater than 1, whichever the one you take, these elements do not fix any compact open normal subgroup here, because if I take this to be G, and consider the corresponding inner automorphism as alpha G, then they have this property. They will take all these elements to, this is 1 and we will go to 1, 0, where alpha G is the inner automorphism. They will be when it is less than 1, not for greater than 1. When it is less than 1, they will be contracting. They are contractions on the vector space part. So they will not fix on the whole space, they cannot fix any compact open subgroup. If they fix a compact open subgroup on the whole group, they have to fix a compact open subgroup on QP also. But then they are contracting, so they will not fix. So our immediate conclusion in the affine group case is that you can't have any power map with a dense image unless K is 1. We look at the third situation, which is the discrete group, such as rationals. So in this case, you always have a compact open subgroup which is normalized. That is the trivial group. It's a discrete space. So the identity is a compact open subgroup. It is always normalized. So in that case also, this previous result does not give us any further information. Whether what happens when you have a power map with surjective or dense image, there is no new information from the previous theorem. There is one more case which I am not mentioning because in that case we know the answer, that is the compact groups. In that case also, the conclusion that normalizing a compact open subgroup is always true. In a compact group, you always have a basis of compact open normal subgroups. Compact totally disconnected locally compact groups have a basis of compact open subgroups normalized by the whole group. So that is not a new information, but in that case, in the compact group case, we know an answer. Pralay Chatterjee has proved there is necessary and sufficient condition in terms of the ordinals. We also have we also have a proof of that result. So I am leaving it out because we already know the answer. So what I said is that 1 and 2, no conclusion, not 1 and 2, 1 and 3, no conclusion can be arrived, but in case of 2, we can decide using the previous theorem. So that means that we need to do little more with this. So we will now recall what is a scale of we will now look into what is the scale function of a TDLC group. We start with a TDLC group. So we are going to list some results. Those are mostly from Willis' paper in 1994. For each automorphism alpha, the scale of alpha is defined to be that particular quantity that is taken over all compact open normal subgroups. So you take any compact of any automorphism of G, when you look at this alpha U for a compact open subgroup, then this is again a compact subgroup and also open. So its intersection with U is a compact open. It's just a intersection of 2 compact subgroups, 2 open subgroups. So it is again a compact open subgroup. And it is contained in U, in alpha U. Alpha U is a compact group and this is open there. So if you look at the corresponding quotient as a quotient space, this has only finite number of elements. So the collection is all integers, finite integers. So a set of non-negative integers always has a minimum element. So that minimum integer is called the scale. Is called the scale. And any compact open subgroup that attains the minimum is called a tidy subgroup of alpha, but we won't be using tidy subgroups much, so only the scale, a very specific property of the scale. For each, so now we have defined the scale for any automorphism, but it is interesting to define the scale for elements also, element of the group also. That is more interesting because it has some additional properties. When one considers the scale for elements of the group, not just for instead of looking at any automorphism. So for an element of the group, you consider the corresponding inner automorphism and look at the scale of the inner automorphism. That scale of the inner automorphism, we will call it the scale of the scale of the elements of the group. So in this situation, now we can easily see one thing, that if the scale of automorphism is 1, scale of the inverse is also 1, which means that this one is 1. That means alpha u is same as alpha u intersection u. That means u would contain alpha u, but scale of alpha inverse is also 1. So you will get the other way around thing also. So you will get that this is true if the scale of alpha and alpha inverse are 1, if and only if alpha fixes a compact open subgroup of the group G. Now we'll see two properties of the scale which are useful. The first one is that scale, though it is defined on automorphisms, automorphism is a group and goes into integers, only non-negative integers. It's actually only to positive integers. So it's not going to be a group homomorphism, but it has this property only. The iterates of the scale is nth power of the scale. This property is true. That is very crucial for us. Then we have that S is continuous on the group. If you restrict the scale to only to the inner automorphisms, then it is continuous. It's not known to be continuous on the entire automorphism group. In fact, it's an open question to find a topology on the automorphism group, so that S is continuous, so that the scale is continuous. So the regular compact open topology or the modified version of compact open topology called Braconier topology, both don't work. So S is continuous on G is another crucial property that we'll be using. So using this, let's just see a proof of how this first result comes. We have a sequence Gn that verify this property. Then you apply scale to this. This is sequence of the group elements. So here the scale restricted to inner automorphism is continuous. So this will converge to, by continuity, this will converge to this. But then this can be written as, by the first property that we have. But all these are integers. This is also an integer. This is also an integer. So that is possible only if this is 1. If it is more than 1, this will diverge to infinity after a finite stage. So this will imply that S of Gn will be equal to 1 for all large n. For large n's, it has to be equal to 1. Even if you can extract a subsequence for which it is greater than 1, then this convergence will not happen. So that's how that other result was proved by Willis. So therefore, this will imply that the scale of G is 1. But then to get invariant compact open subgroup, you need the inverse also to be of the scale 1 here. But then once you have this one, you can put G1 inverse Kn, that will converge to G inverse. You can put plus or minus 1 here. So this way we get that scale is 1, and in other words, G fixes a compact open subgroup. So now, we already know that that first result is not good enough for us. So we'll want to proceed further. So in that direction, we will look at the action of a totally disconnected locally compact group on another totally disconnected locally compact. The simple example is you take any linear subgroup, any subgroup of GL and QP or GL and any other local field. You will get a standard example. So in that situation, we first observe the following. If you have a sequence Gn and G, as in the first one, verifying all these conditions, then G fixes a compact open subgroup of X. Previous one had only this compact open subgroup of G, but we improve it to X for any subgroup that acts on X. for any action on any other subgroup also fixes a compact open subgroup. So in particular, if we restrict to the pk having dense image, then each G in G fixes a compact open subgroup of X. Now we cannot directly apply this technique because now these are not group elements. Suppose pi is the action that defines, alpha is the action that, or pi is the action that defines this G2 automorphism of X. Then scale of pi of G, suppose we have G, K, N converging to G in G, then we can have this one. This is same as scale of but this we will not be able to conclude that this will not converge to scale of this. So this is not in general, we cannot convert because continuity is not promised. Continuity is not promised. So this way directly we cannot apply this. So what we do is that what I generally consider as what I generally call as semi-direct product technique, but it is also the technique that Professor Dani uses in linearization. That is my understanding of linearization techniques, that it's a semi-direct product technique that is used in Dani's linearization also. That you just look at this group, don't look at G, but look at this semi-direct product. Look at the semi-direct product. This is the new group, so we call this as H. Now this is a semi-direct product. As a for topological purposes, it is just the direct product topology, but the group structure is different. Just recall that Gx and Hy, you use this is same as Gx and X G of Y. So the group action is different. So look at this group. Since the topology is the direct product, this is again a totally disconnected locally compact. Now on this, we will now look at the scale of this. Scale corresponding to this group H. So just for the clarity, I'll use this suffix H. We look at the scale of this group. Instead of looking at the scale of G, we look at the scale of H. And this group H has this nice property that G embeds as a closed subgroup of H through this map. G going to G comma identity of the other elements. So this is a closed, the images are closed. This is a closed embedding. So if this property that G and Kn converging to G carries over to that other one also. This one implies treating them as elements. If I'll just leave it as it is. So this will also converge. So now apply the scale. So now this is same as G and Ex to the power Kn, because this embedding is a group homomorphism. It's a group homomorphism. So this is also true. So now you can go to the first result itself. We can go to the first result. So this is, we are now in the situation of the first result. So now we apply this to the scale of H. Then we can conclude that this is 1. So here our conclusion is not about the scale of G. It will come eventually. But we get the scale on the bigger group to be 1. That means on this bigger group, there is a compact open subgroup fixed by this small g. So if you look at the action of this, the conjugate action, it is the same action. You can do this multiplication and verify this. If you simply take G comma Ex and H comma Y, or just an element X, and then inverse of this, since it's already a group homomorphism, I said, so this will be this. You do this, this will be GH G inverse, and this will be simply G of X. So the scale of this will imply that G, the conjugate action, fixes a compact open subgroup of H. Now, G is a small closed subgroup, so it will fix a compact open subgroup of the smaller subgroup also. So we get this result. So instead of directly, we are not able to apply. So we use the semi-direct product technique or linearization technique ideas to conclude this. So in particular, when we apply this to the power map having dense image, each and every element fixes a compact open subgroup of the group on which the original group G acts. So that is something bigger. We'll see in that why it is more important. So now we'll go to the, how does that relates to our situation? How do we obtain this? So it is already known to us that if you have something like fixing a compact open subgroup, there are a particular kind of transformations in dynamical system are called a distal transformation. They have some relation to that. So I have already studied these things much before. So we will recall that notions. We'll restrict our attention to only linear actions. Means when a linear map is distal. A linear map on a vector space over a local field is called a distal. If you look at this orbit, alpha n v, that orbit cannot have 0 as a limit point for any non-zero vector. For the zero vector, this is only just a single point 0. For non-zero vectors, this orbit cannot have 0 as a limit point. So if that is verified, then it is called a distal. So that's called a distal because if you look at two different orbits for two different vectors, E is not equal to W, then this distance will have a positive distance for all n. They will stay away from 0. This distances will stay away from 0. So that's the reason why it's called a distal. So in this case of linear actions, the very fundamental result is that following theorem of this is the following theorem of Ghosh and Ghosh in 1974. G be a subgroup of GLB, then these three conditions are equal. That is, each linear map is distal. Eigenvalues of the linear maps are all of absolute value 1. So these two, 1 and 2 equivalents can be easily seen. But the third one is the odd one. It's not easy to see. There is a G invariant flag of subspaces. That means a finite sequence of increasing subspaces such that all orbits of G in the successive quotients are bounded. All orbits of G in the successive quotients are bounded. Means if you take G, restrict the G action as a subgroup of GLVI mod VI minus 1, call this map as pi I, then this one pi IG closure is a compact group. Is compact. Is a compact group. So that is the thing about it. But the main idea here is first to take finding an invariant subspace. Given any in a finite dimensional vector space, you can always find an invariant subspace for any group actions or for any transformations also. Then you use the fact that eigenvalues are all of absolute value will imply that the trace is bounded. Then apply Burnside density theorem to conclude this. Sorry? Yeah, unipotent, this flag of subspaces, there will be a unipotent group associated to this. So that I'll come to that one, the next one. So these three are equal. So we'll be making use of this result. So with the help of these things, we will obtain a necessary condition. We look at a finite dimensional vector space over a non-Archimedean local field. And G is a TDLC group for which there is some power map, non-trivial power map, which is dense. And a linear representation or a linear action of G is provided. Then through this representation, we provide some necessary condition. So the first one proves that there is a compact open subgroup in V. Now G is acting on V. This is where we are using that fact. We are not considering G to act on GLV. That is also true. But more than that, we consider this representation to G act on V. So V has a compact open subgroup that is fixed by each element of G. So that is enough to conclude that the transformations are distal. Many ways you can conclude that's some other result of mine. That way we can conclude that it is distal. Then by the previous result of Kohns and give us, there is a flag of subspaces with associated unipotent group. I'll define what it is. And a compact group L such that rho G is contained in this L times U. U is normalized by L, will show that. And the flag is L invariant. The flag being L invariant will imply that U is normalized by L. U normalized by L will follow from the fact that flag is L invariant. So given a flag, you can associate a unipotent group to it. We have a flag like this. Increasing sequence of subspaces, starting with the 0 and ending at the whole vector space. Then you can define associated unipotent group. These are transformations on linear transformations on GLV. They are also invertible, that we will see that, such that alpha is identity on the successive quotients on, or maybe x plus vk minus 1 is x plus vk minus 1. That is, if you look at the successive quotients vk by vk minus 1 for all possible case. So it will look like this. The usual unipotent group is for a flag that has one dimensional. Each and every successive subspace is one dimension. That is the usual one, but this is, you may not get the usual one. This will be different. So this is the unipotent group that will be associated to the flag. Now, the flag is L invariant means each of these subspaces are fixed by that maps from L. I'll tell you what this L is also. It's simply that L to be, you take rho G closure, call it LK on Vk mod Vk minus 1. Then LK is a compact subgroup of GL of Vk. GL of Vk. Now L is the direct product of this. So this is like the diagonal element. This will be your compact subgroup L1. For certain number of subspace basis elements, it is L1, then it is L2, and so on, LK. So here you will have the first unipotent and the second step, U2, etc. Last one, there is nothing, it is 1, it's just LK. So this will be your unipotent group. So by our assumption that result that rho of G has bounded orbits, will imply that rho of G is contained in this one. But the L is, I'm restricting to L to this, but in generally you can take the compact subgroup that contains this closure. But I'll restrict to this because of the other sufficient condition I'm trying to get. Because if it is a very large compact group, then that would be a problem. Similarly, the unipotent group also I'll restrict. Because unipotent is a very most general unipotent group associated to a flag. So this is the initial necessary condition I obtained. We obtain this initial condition, then we proceed towards the sufficient condition. So in the sufficient condition, the first result that comes to first result that we recall is a very useful result proved by Dani and Arun. So that is a very useful, but I'm probably stating only a particular case that is required for a totally disconnected group case. So if you take a compact totally disconnected group, L, and the N is any other nilpotent locally compact group, suppose L acts on N, and the action is linear over a field F. Over a field F means, if you look at the central series or any series, the successive quotient is a vector space over the field F. And the action are by linear maps on the successive quotients. So that is very crucial. So if that happens, and in addition, we have to have this pk to be surjective on L. Otherwise, we cannot conclude anything here. So pk is surjective on L, and k is co-prime to the characteristic of F. Under these two conditions, we can conclude that the power map is surjective on the semi-direct product. So this is actually a semi-direct product, L and U. U is a normal subgroup, and L is normalized as U. So U is a normal subgroup in this product. So whenever you have a product, if one of them is a normal subgroup, then it is a semi-direct product. You can think of it as a semi-direct product. These are standard materials in topological groups. So in our situation, we can make that conclusion, provided we get pk to be surjective on L. That means on this one. So that's the reason why we restrict our attention to rho G closure. Because on G, it is power map is surjective. It's dense, but this is compact. So it's on closure also it is dense, but it is being compact. The dense and surjectivity are the same. Is that clear? This one. Yeah, you can take any of these groups are the simple examples. Standard, you take 4x4 matrix. I can consider GL2ZP and other vectors here, then another GL2ZP, some other vectors here. So 4x4 matrix. Below it is 0, above here it is star. On this 2x2 thing, there is something there. This will be an example. This is another more general example is this one. Any flag corresponding unipotent group and this kind of compact group, but you have to choose the compact group to have the map surjective. K has to be co-prime to the characteristic of F, which will be true if in the case of QP, because it has characteristic 0. So K will be co-prime to that characteristic. So we apply this to extend our necessary condition further. Yes. We look at the same situation as in the necessary condition. Here, the first thing we modify is that We assume that rho G is contained in LU, and further we assume rho G U is dense in LU. That means this condition will be put in. LK to be rho G closure. So in that case, we first conclude that PK is surjective on the compact group L, and then we conclude that when K is co-prime to the characteristic of F, this is any general non-Archimedean local field. So you have the field of Lorentz series over a finite field are also included. So in that case, PK will be surjective on LU, though we are not able to say much about on G itself, but G will be contained in a bigger group on which the power map is surjective. That bigger group is very close to that group. In case if the characteristic is here, first condition, it is co-prime to the characteristic of F. In case if the characteristic divides that integer K, then rho will become finite. Rho of G will be finite. Now, in the case of when characteristic divides K, you can divide the entire situation into two different ones. When it divides K, then it is done. We already done. When it doesn't divide K, we look at the residual characteristic, and now we get two different cases. One, when the residual characteristic divides K, in which case the compact group will be finite because L is a compact subgroup of a linear group over a non-Archimedean local field. It will have a open subgroup which are probe P finite. If P is the residual characteristic. But then probe P groups cannot have any power map to be surjective if that K is divided by P. So we get that L is finite and the rho of G is contained in a finite extension of a split unipotent algebraic group. Split unipotent means the success in the unipotent case, there is a central series and the successive quotients are vector spaces. So those are now vector space. Those are in general, it is not the case. So here it will be a vector space. So such a unipotent group will be called a split unipotent algebraic group. PK is dense in the intersection of rho G intersection U. That is the additional thing that we can conclude. In case if the characteristic is positive, when it doesn't divide K and the characteristic is positive, then you can conclude rho G itself to be finite because this part will also be finite. Unipotent group will also become finite. This is the residual characteristic. Now, using the main result, we can derive very similar results for Lie groups over any non-Archimedean local field. I'll quickly go through this because these results are very similar to what we have seen in the other theorems. First thing we conclude is that G is of type R. Type R is a group that I am very much interested in. These are groups where the adjoint representation. What is the use of Lie groups and over representations? In Lie groups, we generally have a representation, which is the adjoint representation. So using the adjoint representation, we conclude that we look at adjoint representation and make this conclusion. And the first one is that G is of type R. That means adjoint map eigenvalues of each and every adjoint element as is of absolute value 1. That is the G is of type R, just rewording of that property. Second thing is that adjoint of G is contained in a compact extension of a unipotent normal subgroup. That means this one, this is what I am saying. Compact extension of unipotent normal subgroup. Third one is, if G is compactly generated, then G is adcompact. That means the adjoint image, this one, will itself is a compact group because this unipotent group, any compact subgroup, any compact set contained in the unipotent subgroup generates a compact group. That's a property that we'll be exploiting to conclude that if G is compactly generated and there is a power map that has dense image, then you can conclude that G is adcompact. Using this, it is contained in a compact extension. A similar result that, as I stated previously, you can derive this for using the adjoint representation. All these are, yes. Compactly generated means there is a compact set. The group that is generated by that compact set is the whole group. That simply means that there is a compact set K contained in G such that G is the group generated by the compact set, or it's a union of this Kn, K union K minus the power n. We'll assume that identity is there inside. So we can derive all the similar results using the adjoint representation, in particular for rho. So now we'll look at, yes? Distality, we get it previously right at the beginning itself, when we proved that first proposition. Yeah, that is, distality is what is applied to this to derive all these results. To derive all these results is distality, and the cones give us this theorem. Now we'll go to algebraic groups. In algebraic groups, we have much stronger conditions. So we look at algebraic groups over any non-Archimedean local field. We are not considering the real case, only the periodic or Lorentz series over finite field. So here the main result is, suppose the characteristic of F does not divide K, then we prove that the density of the power map is same as the surjectivity of the power map, and they are equivalent to proving that the reductive Levy subgroup is compact and the power map is surjective on that reductive part. Reductive part is compact. Once it is compact, we already know how to get a necessary and sufficient condition on that. So on that compact group, it is surjective. So this is, we proved it for any non-Archimedean local field, but this result is already proved by Chatterjee in 2009 for the periodic case. It means the characteristic zero case. The next results are also known in the periodic case, I suppose. This result is as a result of the previous theorem. We obtain some basic properties, like if the power map is surjective on the group, can it go down to any other subgroup also? But you cannot expect it to go to any other subgroup, because we know that example on integers there is no surjectivity, but on the whole real line it is there. Similar thing you can do it in QP also, ZP and QP. QP there are surjective maps, but on ZP you cannot expect surjectivity to hold. Not for every case. For some case it will work, but for some other case it will not work. So we know that it's not going to work for every subgroup, but if we look at algebraic subgroups, it does work. The surjectivity passes on to. You don't have to look at density because they are the same in the algebraic group case. Second result is looking at the converse of this. Suppose you have an algebraic group on which the power map is surjective, and also on the corresponding quotient also it has surjective, then can it be surjective on the original group? So that is, the answer is yes, but here we can relax the algebraic condition, but we can consider any closed normal subgroup. PK is dense. Here we make it dense because here density and surjectivity are different for general groups, but for algebraic groups they are the same. So PK is surjective on the group of rational points. So there are some other results that I have done, so they are interesting on their own. Very similar results, that any compactly generated linear group for which the power map is dense is compact. If you take any compactly generated linear group over a non-Archimedean local field, not the real case, over a non-Archimedean local field, then you will have this property. If linear group means a closed subgroup of GLV. Take any closed subgroup of GLV. Suppose the power map is dense image, and if G is compactly generated, this is dense, then by this G will be contained in a of this form L times U, where L normalizes U. Now G is generated by this compact set. I'll give you a proof of this. So K is contained in L times U, and L is a compact set. So K will be contained in L times U intersection K. U intersection K, or be contained in some other compact subgroup, may not be K intersection U. Contained in a compact set where U, this is, I'll call it C. C is a compact set in U. C is a compact set in U. Now on unipotent groups, any compact set generates a compact group. For instance, a simple case is the QP or the Lorentz series for a finite field. In both the cases, if you look at any element or any X in QP, then this additive group generated by this will be XZP. A similar thing you can write here. XAP. Yes. ZP is the, or AP. This will consist of all vectors B such that they have valuation. Norm is less than or equal to 1. So this is in one-dimensional, but the same thing can be done for unipotent group also, because on successive quotients, you can have vector spaces. So you can lift all of that to the whole group. It is contained in L times C. Now L is a compact group that acts on this unipotent group. That's a regular conjugate action. So this compact set that you choose, you can choose in such a way that it is normalized by all L in L, by all transformations from L. Because L is a compact group, so you can choose a compact set that is normalizes this compact set. Now this compact set generates a compact group. So that also I'll denote it by the same C. So it is a compact subgroup. So L normalizes the compact subgroup. So it is a group. So LC will be the compact group. So any compactly generated set contained in a group of this form L times U, where L is a compact group and U is a unipotent, split unipotent group. That is more important in the positive characteristic cases. So any compact set will be contained in a compact group. So that is generally a compactly generated linear group for which PK is dense, is compact. Similar results can be proved for linear groups over local fields also. I'll give one sample result. Again, we use the representations only, natural representations. So you look at a global field and a subgroup of GLDE. E is the global field. Take any subgroup. Suppose PK is surjective. This is a discrete group. This will be a discrete group. So no point in saying dense. It's better to say it's surjective on H. For some K greater than 1, then H contains a unipotent normal subgroup of finite index. H contains a unipotent normal subgroup of finite index. If you have a subgroup of linear subgroup of over a global field simple example is Q. Easy example is Q or FP. It's a finite field. Nice example is Q. This will be your global field. Now the technique here is, now if you look at this Q, then it embeds into any QP also. There is a natural inclusion into QP for every prime number. The interesting fact is that if you do this thing, then for each P there is a representation. So there will be a representation from GLQ to GLQP. N dimension means N dimension. So you apply that previous result for each of these P's. For each of these P's, then you can conclude that the compact subgroup becomes trivial. It's finite. And the compact subgroup becomes finite. But you don't actually apply for each and every P. You choose a prime number which divides that K. Then you can apply that previous result to that. If P divides K, then the compact subgroup is finite. If P divides K, this is the zero characteristic case. The characteristic F does not divide K. But if P divides K, the compact group becomes finite. So you choose a P that divides K, then you can get the compact subgroup to be finite. So H is contained in a unipotent normal subgroup. Similar, various other results similar to what we have seen for algebraic groups and other general results can be proved for subgroups, linear groups over global fields also. So the same result, now we have seen that the power map to be surjective or dense on the whole group. Instead of assuming this on the whole group, you can assume that the power map to be surjective or dense on a lattice, that means a finite co-volume subgroup or a co-compact subgroup, and to make these conclusions. So same conclusion can be derived by assuming that the power map is dense in this subgroup, which either it has finite co-volume or it's a co-compact subgroup. Then you can see that all the properties remain valid. In this situation also. And these are the references that I have used. Pralay Chatterjee, 2009. Coates and Givas, 1974. Dani and Mandel, 2017. Mandel and Raja is reprint in 20. Bill is in 94 paper, but probably uses the other subsequent papers also. Thank you. I also want to wish Dani happy birthday.
And comments?
Oh, only in this slide or in the other slides? All the slides are that. That because these slides were all prepared for my 2014 talk in Mathematical Institute, IMSC, on expansive automorphism. So probably I didn't remove the title. The subtitle or something like that. Now only I'm noticing. Algebraic, yes. How does that help? How the algebraic thing helps? This is the thing that you are asking. How does the algebraic thing helps? It's because then you have this property for algebraic groups only. That surjectivity is same as looking at the reductive Levy part. That's how we use this fact for algebraic groups only. Not for general groups, we cannot define a split unipotent radical. The previous class, previous necessary and sufficient conditions used in it.
Yeah, any other questions?
Scale is not continuous. That is called a Braconier topology. No, I'll write down. It's very similar to compact open topology only, but it may be different in some cases. It considers one more set of bases That is, usual compact open topology consists of all alpha such that alpha k is contained in open. Now you consider alpha inverse k also contained in open. This is another set of bases. Not the same thing. Same set has to satisfy two conditions, but this is one set. This you can call it n ko, and this you can call it n minus ko. Along with this, it's called a Braconier, but most of the times these are the same, but some cases it is different. No, it would not that case. No, that is a very general situation you have. That is not. I'm not too familiar with this, but you can browse and find that.
Yeah. Okay.
Yeah, that is, yes, but I don't think I can tell you what those results are. Either Dani or Arun or Pralay, they can tell you what exactly those results.
Any other? Yeah, if not, please thanks the speaker again.